Okay. Hello, guys. No, it's fine. Wait. Okay. Don't. Okay. Hello, guys. Welcome. Does it up to where does it see now? Cool.
Yeah.
All right. Cool. Nice. Thank you guys for joining us. If you're joining us through the live stream, if you can say hi in chat to make sure you can hear me, I would appreciate that. Just to make sure everything's working. I'll give you guys a couple of seconds because I do know the stream is delayed. But we do have a couple of people with us live, so we'll have some interaction. Audio kind of low.
Should I raise it?
Yeah, let's just raise it a tad bit.
No, I'll do it a tad bit. Okay. Ask how it is. How is it?
Yeah, can you let us know how the audio is now, just to make sure? Should be picking up the one from the mic. By the way, guys, if you haven't signed in, I recommend it. It should be the QR code that's on the screen right now. Use that, sign up.
A little better.
A little better, okay. Scan the QR code and then sign up, just so we can track your participation. And then when we get to actual competitions, Gary knows how to split you up to accurate team sizes, for, depending on dedication, which will help out a lot. Okay, anyways, so what are we talking about today? Yesterday, Gary gave a lecture on the longest common subsequence, which is a pretty common dynamic programming problem, and really important to know how to solve it, because you might see it in an interview. So let's start off with the problem. We're given two strings. Let's say the first string is alphabet. And then the second string is habitat. There we go. So from these two strings, we want to find the longest common subsequence. Now this subsequence does not have to be contiguous. So this, the strings don't have to be all next to each other. It can be spread around. So let me give you an example of how, what the answer will look like here. The answer here will be H, A, B, and then T. The reason for that is because in the alphabet, it has no character in common with the second string, habitat, up until it gets to the H. From there, the H and H, that's in common. A and A, that's in common. B and B, that's also in common. Then the next character that is in common is that T. So the longest common subsequence for these two strings would be habt, or H-A-B-T. Does that make sense so far to you guys?
Yeah, very good. I like your handwriting.
Thank you. Let me just zoom in just a tad bit to make sure it's visible. Perfect. All right, so we were able to do this, but obviously we didn't come up with an algorithm, which is what we want to find. So a computer can do it and not us. So the first thing, well, first off, I am going to erase this. The first thing I want to go over is, how did a human solve it? So we can figure out exactly how I solved it, then maybe we can create an algorithm that mimics the way we did it. Let me give myself some more room. There we go. So now let's see how I did it. I'm going to start off from the end here, and then I'm going to be moving to the left. So to find the correct answer, I want to first look at these last two characters. I want to ask myself, are they similar? Well, they are similar, so I know that could be part of my answer. Therefore, I'm going to add it. Now, I can move one down, and I'm looking at everything up to habitat and alphabet. The A and E are not similar, so I know I can ignore that. And then I know the A and B here are not similar, or the E and T is not similar. So I can continue moving down until I find another character that they both have in common. In this case, it's going to be the B. So I moved all the way down until I found the B in alphabet and the B in habitat. And I marked that as part of my answer. Continue following these steps. I can see that A and A match. I add that to my answer. Then H and H match. I add that to my answer. Now, of course, this is only one subsequence. You might find multiple, but you have to find the longest one. Yeah, question?
Why is your first instinct to start from the end of the string towards the beginning of the string?
So starting from the beginning of the string, it's also going to be the exact same thing. It's going to provide you the same answer. The reason I specifically did it from the end is because I'm going to start off with a recursive solution, and that starts off from the end. So I'm trying to tie everything all around. But good question, yeah. Doesn't really matter. That's the answer. And in case you guys didn't hear it, the question was, why did I start at the end? You can start from the beginning. It'll be the same thing. So one very important thing that you might see here is that when I found a match, I moved down, and I no longer considered the two characters that matched. Why? I want to ask you guys that question. Let me read chat to make sure.
Yeah, you're talking about that.
What about the last T in habitat? So, very good point. The T could be either coming from this last T or the first T. And it'll give you the exact same answer. So it doesn't really matter where the T comes from, because it will give you the same thing. But good, that was a good question. All right, let me make sure there's no other questions. There isn't, nice. All right, so going back to my other question is, when we found a match for two characters, why did I continue looking down? Why did I not stay at the character that matched and try to match it with another character? No?
Wait, repeat the question?
Okay, yeah. So if two characters match, for example, why did I move down? Why did I not stay at that character that matched and try to match it with something else?
You want to find, like, the final string is formed from the character in the first string and the character from the second string. So you need both characters in order to add that character to the final string.
And can I use one character multiple times?
No, you cannot.
No.
Yeah,
Okay.
that's part of the problem.
Exactly. You cannot use one character multiple times. For example, here we have one T, and then in habitat we have two T's. Our answer we cannot match this one T in alphabet to the two T's in habitat. The only way to do that is if we had another T here. We can match the first T to the first T, then the second T to the second T. But since we don't have that, we cannot use that T multiple times. Let me read chat one more time. Because you can't repeat. Exactly. Perfect. Thank you. Yeah. So we know that, right? We can't repeat. Let's write that down. That could be part of our algorithm. Okay, yeah. So if the character at some position n equals the character in the second string at some position m, if they're equal to each other, we know that it cannot be repeated, so we need to move n down by 1 and m down by 1. Minus equal 1, minus equal 1. So just in case this looks confusing, let's run through an example of it. Here, when I was looking at these last two t's, what was m? Oh, actually, sorry. Have it flipped around. What was n when I was looking at this t here?
And was the length of the first string?
-1.
-1.
Yeah, for this, so let's just count by ones.
Yeah.
So not 0 indexed. So this is 1, 2, 3, 4, 5, 6, 7, 8. When I was looking at t in alphabet, I was at position 8. What about the t in the second string? What would m be?
7.
7?
Yes, I counted in something.
You agree with 7? Okay.
Yeah, so
You don't think I can count?
1, 2. I want engagement from everyone. 1, 2, 3, 4, 5, 6, 7. Perfect. So when n was equal to 8 and m was equal to 7, S1 of n, aka, let me do this in a different color. AKA S1 of 8 equals S2 of 7. What is this going to return?
But there was a match.
It's going to return that there was a match. Perfect. It's going to return true because S1 of 8 is this t, and then S2 of 7 is this t. And that character is equal to each other, so it's going to return true. And then now we know, because we were doing it manually in the beginning, when there's a match, we know we cannot repeat it, so let's move down. Perfect. So that we kind of drew this, and now we know this is part of our algorithm. This might help us. What's something else that could help us? Let's say there's not a match, right? When there is a match, we already figured it out, and we know exactly what to do. But what if there isn't a match? So this solution is to start at the end. This is one solution, which is going to be recursively.
Yeah, so why do we start with 1 instead of 0? Convention for this problem.
Yeah, for this problem, you could start at 0, and then this would be 0, 1, 2, 3, 4, 5, 6, 7. And this will be 0, 1, 2, 3, 4, 5, and 6. So it's just going to be -1 for these two. But for this specific problem, I just wanted to start at 1 because something that we're used to, start counting at 1. But in reality, no real difference. In your algorithm, you might have to do a slight change. Instead of like S1 of n, where n is the size of the string, you might have to do S1 of n minus 1. So very small change, not that big of a deal. Okay, so let's go back to my question. If there's not a match, what do we want to do? Let's see if you guys know this.
Well,
Right. Okay.
should we say it if we already know it? Or give them some time to like...
Yeah, tell me why.
So the first step in the dynamic programming approach, you want to look through all the different possibilities. So the first step in the dynamic programming approach, you want to go through all the possibilities. So in this case, n at 8 and m at 7 do match. So it'll go to E and A. But because E and A do not match, you're going to want to explore the possibility of what if we went back one number in m, and the other possibility where what if we went back a number at m separately, so recursively.
Yeah, perfect. So that's exactly it. So when we do match, we know we want to move down and look at the character before it. But now, as you can see, A and E does not match. And what he just said is, if any A and E does not match, then maybe we want to move m down by 1 and see if there is an e in the second in S of 2. So stay here looking at e. So stay here looking at e. And we know that e does not equal to a. They're different characters. So maybe try moving a down. E does not equal to t. So now we can continue. We might want to continue moving this down. And that's one approach we can do, where we try to find the e in the second string. Or maybe that never works out. Maybe we can do the opposite, where we know e and a does not match, but instead of moving a, we move e. A and b does not match. A and a does match. So in this case, the right thing to do was to move n down by 1. But we never really know which one we want to move first. We don't know if we want to move m or if we want to move n. That's why we need to try both. Let me make sure there's no question. Yeah.
We do recursion,
Exactly. So we do recursion, yes.
You know what would be a good idea is if you grab your phone and open up the stream there, you could perch it up on the left.
Ah, you're a genius.
But you
Okay, next time, yeah. That's actually really smart, but next time, yeah. Damn, that's good. Thank you. If you guys didn't hear it, he said to put my phone here so I can read the chat of the stream instead of having to go to the computer.
Yeah.
Right, brilliant idea. I'll do that next time for sure. So going back to this. When they do not match, we know we either need to move down n by 1 or move down m by 1. In this case, the right thing to do was to move down n. And we eventually found a match. So we could add that down and add it right here to our statements that we'll be using for creating our algorithm later on. But first, let's go through with this. And let's see if with just these 3 rules, the rule where if they're equal to each other, move both of them by 1. If they're not equal to each other, move one down by 1, or move the other down by 1. Let's see if that's enough. So we start off at the end. We're looking at t, and then looking at t. N and m, n is equal to 8, m is equal to 7. They are equal to each other. So let's just, for now, in another variable called answer, let's write down that t. When they're equal to each other, we know we need to remove it down by 1, both of them. So now n goes to 7 and m goes to 6. They're not equal to each other, so we have to try one of 2 things. Either move down n by 1 or m by 1. And of course, when it comes to this point, we don't know which one we want to move down. We can't really tell, so we have to try both. Me, just by looking at it, I could tell, and we know that the answer will be to move down n. So when n is equal to 5, that's when we get our next match. Then, of course, we add that to our answer. Now we move both of them down by 1. This becomes 4, this becomes 5. Now we're looking at the T, the first T in habitat. Now we're looking at H in alphabet. Here we have another example when they don't match. So once again, we have to move both of them, either the top one, either n down by 1 or m down by 1. Here, what do you guys think is the right answer? Just by looking at it. I know the algorithm will try both, but which one should we do specifically right here to get our next match?
We should move m.
Sorry?
We should move m.
We should move m? Yeah. You know, something I noticed? is that we're also missing a b. So back here when we were at the e and the a. Yeah, when we were at the e and the a, the right thing would have been to move n down to b, and then eventually move down m to this first b. That's where we would have gone the b in our answer. And since we're doing this recursively, it would have come back to that e and that a. And now we continue moving this one down all the way to the a. So we did miss a b. If that didn't make sense, just give me 1 second. The reason we had to do that is because we're doing this recursively, where it tries both of them, and then it comes back to that node in the recursive tree. So from here, we know the next point, 5, 1, 2, 3, 4, 5. We're at t, 1, 2, 3, 4, and we're at h. Now here, we move down m. We continue moving down m all the way until it is 1. And then that's where we get our final match. So we know that with this, we know that it will work. And we know that that's another logic that we could add for our algorithm right here. Let me actually write it down. Else what? Let me ask you guys. If they don't match, can they see? Yeah, cool. Else, if they don't match, what do we want to do?
Once again, if they don't match, you want to explore like the rest of the possibilities. Since right now, do we have a grasp of the problem yet? Because
yeah, you can say recursively. It's fine.
Oh, okay. In that case, you can do 2 calls to look for Sn minus 1 and S2m and Sn and S2m. Wait, I get confused. Yeah.
Yeah. No.
But
Yeah.
That's it.
Yeah. Let's just say we're only including the n and the m. And the S1 and S2 is global variable, whatever.
Yeah.
Let's say we do match. We have to move both down.
Yeah. So let me change this to solve. There we go. Okay, cool. Awesome. So if they do match, we want to move both of them down because we cannot repeat that character. So that's where this comes in. Let's say solve is this function that we're using to solve this problem. Else, if they don't match, let's try solving it when we move m down just by 1. Or let's try solving it if we move n down just by 1. And of course, here we want to take the maximum answer that it gives us. So solve is going to return some number, and we're going to choose the one that's greater either from when we move m down by 1 or n down by 1.
That seems perfect and foolproof.
Yeah, this looks perfect, right, guys? No, not really. Let's go over why. Did I do n first? I did do n first. So when we are inside of this function, they can see this, right? Yeah, okay, cool. When we're inside of this function, we have 2 variables, n and then m. This function could return 3 things. It could either call itself with n minus 1, m minus 1, or it could call itself with n and m minus 1. Or finally, it can do n minus 1 m. So there's 3 calls that this function can do. So let's add that. When we're inside of here, remember it called itself. So now it's going to be calling itself solve right here with n minus 1, m minus 1. The issue now is that this can also call itself 3 times. Can they see up to here?
Yeah. Wait.
Yeah. Let us zoom the camera. No, zoom. Adjust. There we go.
I think they can see that now.
They can see up to here?
Yeah.
Yeah, perfect. They can see my finger. Nice. So let's go over the issue one more time. When we're here, when it calls itself with n minus 1 and m minus 1, which is this block right here, this could also call itself 3 times. So let me write that out to show you guys how it would look like. Does everyone agree with this? When we're inside of this block, n minus 1, m minus 1, it can call itself 3 times. And when it calls itself, it will be n minus 2, m minus 2, n minus 1, m minus 2, then n minus 2, m minus 1. You guys agree? Yeah, that's one nod. David, you're nodding too. Perfect.
Yeah.
All right, let me. Do you want to come up here?
Huh?
Do you want to come up here?
For what?
I'm going to ask you a question.
Oh, yes.
Okay. So I'm also going to give you, yeah, also going to give you the marker. And I want you to explain why it's n minus 2, m minus 2.
This is the call where these two match. So it'd be this one, right?
Sorry, say that again.
So this is the call where, for example, T and T match.
Yes,
so
yes,
it's,
yes.
it's this one.
Yes.
Yeah.
Can you talk again?
You can see what he's writing.
Wait, can you talk again?
I wasn't writing anything.
Say something?
Hi.
You say something?
Hello?
Okay. You're more audible than him, but like.
Yeah, because like he has the microphone. But it's okay. You can explain.
No, it's fine. Go continue.
Yeah, so
I want
like
you to do it.
This call is when both the letters match, so it's calling this one. So we're going from I'm gonna
Yeah, go
redo
ahead.
what you do. We're going from these over to the next two. And wait, next two?
Yeah.
Wait a sec.
That's why I'm asking. Yeah.
Is it? Oh, it's because of.
Yeah.
Oh well, okay.
So explain why it's minus 2.
Are you missing something here?
No.
No. Wouldn't it be because you're storing the values of how many letters we have matched so far?
No, it's because, I'm sorry.
No, it's okay.
It's because we started with n and m, right?
Yeah.
But now we're doing this call, n minus 1, m minus 1.
Yeah.
So now we're here.
Yeah.
We started with whatever we started with, minus 1, and whatever m we started with, minus 2.
Yeah.
Now we're saying that it matched again.
Yeah.
So now we're doing n minus 1, which is part of this n,
Oh.
minus 1.
Okay. Yeah.
So now that's what turns it into n minus 2, m minus 2.
Yeah, that makes sense.
Yeah, yeah. It's exactly. It's n minus 1 minus 1. And then m minus 1 minus 1.
Yeah, that makes sense.
Thank you.
Here. Yeah, of course.
David, you're next, so.
I'm next.
Yeah. Okay, cool. So it's with the exact same thing here with why this is only minus 1, this is minus 2. Because let's say they don't match, we're going to be calling this one right here. Where n does not change but m does. Here our n is n minus 1, and our m is m minus 2. So this is going to evaluate to n minus 1, and then m minus 1 minus 1. That's why we get n minus 1, m minus 2. Hopefully all of this m's and n's is not confusing.
I have a question.
I have a question, okay.
N minus 2 because you're moving down 2 letters. So
Exactly, yeah, n minus 2 because it matched twice, and we did minus 1 twice. So this is the first time we did minus 1, and then it matched again, so we have to do another minus 1, and that's where we get the n minus 2. All right, so hopefully now all of this makes sense of why some of them are only minus 1 and the others are minus 2. So let's continue building out how this recursion tree will look like. So when it calls itself with n minus 1, m minus 1, it also has 3 other calls it can make. It could be n minus 1, m minus 2. It could also be n, m minus 2. And it could be n minus 1, m minus 1. Can they see up to here?
yeah, no, it cannot.
Just move the camera. Zoom it out a little bit more for you guys. There we go.
Okay. Must be watching it.
Thank you. Perfect. So now with n and m minus 1, it can make the 3 calls, and the next 3 calls are going to be this. If they match, subtract 1. So now it becomes n minus 1, m minus 2. If it doesn't match, only subtract 1 from m. So now it becomes n, m minus 2. Or subtract 1 from n. So it becomes n minus 1, and then m we leave the same. So it's just m minus 1. What do you guys see here? Is there anything repeating itself here?
So yes, n minus 1, n minus 1, and you see it again?
Okay, perfect. Come up here and circle where it repeats itself.
All right, guys.
Let me stand here so they're close to your mouth.
Yeah, you saw me every Wednesday. So, look at this right here. This, we already saw this, look. They're repeating themselves, and also this one, and this one. You're recalculating the values. So you're getting it, you're calculating it multiple times.
Yeah.
And that's inefficient. That's the point.
There's actually one more.
Oh, there's one
No,
more.
I'm kidding.
Okay.
No, no.
I was going crazy then.
Yeah, no, because there's no other n minus 1. Yeah, no. N minus 1. Yeah, no, that's it. So is this efficient? Is it efficient recalculating work and then redoing it again, maybe millions of times, hundreds of times? You guys think it's efficient?
It's extremely inefficient.
Extremely inefficient, okay.
This is exponential.
Oh, okay, that's a good word. That's what I'm going to get into next, okay.
Wait, just out of curiosity, is exponential like the worst it can get, or can it get worse?
I think factorial.
I think factorial is worse, yeah.
And n to the n.
Yeah, and n to the n is also bad. Okay, so let's see.
No, it is not efficient.
No, it is not efficient. Yep, you're 100% correct. So this is actually exponential, like David said. It's extremely bad because we might have to do this work multiple times, which could result in doing it hundreds of times, thousands of times, or millions of times. I'm not exactly sure the time complexity of this algorithm, but if I had to take a guess, worst case scenario, they never match, and it's always going to call itself twice. So I believe the time complexity be 2 to the m times n. We're multiplying the length, the first string, times the length of the second string. It's either that or m plus m. It's one of these two. But it's exponential. That's the point. And it's bad. That's also the point. So what can we do? Instead of redoing this work multiple times, is it possible for us to store it somewhere? So when we get to a block or a n and m pair that we've previously seen, we don't do the work again. Instead, we can just get whatever that answer gave us. Is that possible? To store the work of a repeating function call somewhere? Okay, that's one nod. What do you think, David? Is it possible to store this work somewhere? Maybe in a table or something like that?
Yes, in a table.
Yes, in a table? Okay. Maybe not in a physical table like those, but yes. We could store this information. Okay, I'll leave that. So let's say we did this n minus 1, and we also did this n minus 2. But now here in the second n minus 1, because remember, these two are the exact same. Wait, no, sorry. These two are the exact same. Instead of doing the work again for something that we've done before, the first time we do it, let's just store that information. So let's say when we saw n minus 1, and n minus 2, let's save whatever answer that gave us. Let's say that answer was 2. So now the next time we see n minus 1, n minus 2, which is right here, instead of doing the work, we can first check if the table has the solution already. And if the table has the solution already, let's not do the work. Let's just return whatever answer the table has stored, which in this case will be 2. So why does that matter? Well, it matters a lot because it can lead us from being inefficient to efficient. Here, if we didn't check the table and the table didn't have a value, we'll be making 3 other calls. But if we do use a table and there is a value, we don't have to make these 3 calls. Instead, oh, actually I should have left that. Instead, we can just return whatever the table has, and we never have to make those 3 calls. This can lead us to being efficient. Are you guys comfortable with programming this? Do you guys feel like you have some understanding about how to set this up?
Yeah, it's just a 2D array, right?
Yeah, you could do a 2D array. You could also do a hash table.
Oh, yeah, true.
What will you be doing? You'll be doing it recursively, right?
I mean, at first, yeah.
At first, yeah. At first, it's recursive. We'll talk about the non-recursive part later. But at first, we'll be doing it recursively. You agree, David? Recursive using 2D matrix.
Yeah, like Gary said, you get the recursive solution first, and then once you've developed the recursive in a base case, you can develop a non-recursive out of that.
Yep, exactly. So as Gary said, we can get the recurrence relation from the recursive solution and then make the non-recursive slide. So you guys agreed doing it recursively?
Yep.
Is there something missing if we want to do it recursively?
We need a base case.
We need a base case, yes. So I'm going to erase this recursive tree right here. I'm actually going to write out the function. Let's leave it up to the viewers in the live stream. What should I name the function? We can do solve, LCS for longest common subsequence.
Hey guys, LCS?
Or longest length of longest common subsequence, LCS, which I know Geary did in his class.
Let's just, I'm going to make sure they can hear. Let's make it LLCS.
LCS? Okay, I think she said LCS.
Okay, LCS.
You went against David, plus 10 points.
Oh,
No, I'm kidding.
What?
Okay, so let's call it def LCS. Let's say, like remember, let's pretend these two strings, global variables, so let's not add it to our function. What we do want to add is n and m. You know, now that I'm thinking about it, I think Geary, for his slides, he had it backwards. I think he had m and then n.
No, I think it was.
No, you did actually. The M was the first length.
He did?
N.
Okay.
It doesn't matter.
Yeah, it doesn't matter, but
We're already on that. N is S1 and M
Yeah.
is S2.
so, but just in case you guys are in Gary's classroom and you're trying to compare what I'm talking about to his slides, just know that I chose n to be the length of the first string and m to be the length of the second string.
Or indexing.
Or indexing. Okay, cool. So we made our function. We call it LCS. It has two arguments, n and m. We all agree that this would be a recursive, right? And we know what to do. We kind of have an idea of what to do. So let's say they do match. Let's write that down. This is pretty simple in itself. So we can actually just copy this and put it over here. If s of 1 at index n, if that character is equal to s of 2 at index m, if these two characters are equal to each other, then let's return what? Don't say it. Okay, if you don't remember, then you could say it.
Actually, I wanted to add something. Maybe we should tabulate it and then return the tabulated answer.
Maybe.
Yeah. Let's add let's add the memorization after.
Oh.
Yeah.
I was gonna say maybe just like put where you're gonna put there, and then leave some space for when you want to show the
race case.
Oh. Okay.
Yeah, I might need more space than this
Leave
though.
some space so that you can show the recursive solution with tabulation.
Yeah, you're totally right. I am going to need more space for that. Okay, cool. So if they match, what do we return?
1 plus. So now it returns a number, so 1 plus.
Yeah, so it matched, so we know that that is going to be part of our answer. So what we want to do is 1 plus calling it itself. Calling it itself, and of course, moving n and m down by 1. You guys agree with this? Yes? Okay. And once again, the reason why we're doing plus 1 is because we want to get the longest covered subsequence, and this function is returning an integer. So since there was a match, we know we can add it. Let's just add 1, and let's see what the rest gives us. Any questions from the live stream? No? Okay. Also, can you take off the QR code? Thank you. Yeah.
Oh, that, yeah.
Thank you. So now let's write the other part where it doesn't match. Else, what? Else we know that we are calling n minus 1, and we're also going to be calling n minus 1 m. These two are going to give us some number, and since we want the longest, the length of the longest common subsequence, that was hard to say. We know that we want to get the maximum between one of these two. So that is what we want to do here. We want to return the max between calling solve with n minus 1, calling solve with n minus 1, m. Does that make sense to you guys?
Yeah.
Yes?
Yeah.
David, you too? Perfect. Let's add our base case. What would it be? No, it's not. Yeah, check the chat as well. Oh, you want to say it?
No, I was asking because I like.
What? Yeah. Yeah, go ahead, type. Oh, can you type? Okay, it's fine. Alejandro got it. So it's our base case is if we want to check if n is equal to 0 or m is equal to 0. Let's remember we're indexing with 1. So at 1, they can still match, but 0 is just out of bounds, and we know we can stop there. So let's do that. Wow, that was really bad. So if n is equal to 0 or m is equal to 0, return 0. You guys agree? Yeah?
I agree, but you need to remind people that like the indexing starts at 0, so you need to be like really careful with that.
Yeah.
Hold on, does it start?
No, here it's starting on 1.
We're starting on 1.
Yeah, but I'm just saying like when you're actually gonna go code it.
Yeah.
It starts at 0 unless you're coding like
Yeah.
some weird language.
When you actually when you're actually programming it, instead of n is equal to 0, you might have to do if n is less than 0. Or equal to -1.
Well, we are starting at 1 in our string.
Yeah, exactly.
Yeah.
Let me. There we go. So we're starting at 1. Then we're starting at 1. Cool. So we have our base case. We have our recursion. Is this the efficient implementation of this program? Okay, someone in chat said no. Someone called David Acosta. He has the same name as you do. That's really suspicious.
What a coincidence.
Yeah, what a coincidence. I wonder if he answered no before the stream caught up to my question. You can tell the future now. Okay, so yeah, you're totally right. This is not efficient because although we have a base case, that's just stopping us from making this an infinite recursion call. But still, we're calling itself. We can call the same numbers, the same n and m, multiple times. So we need to implement that table. Let's say that table it's created somewhere. Let's call it m. No, we cannot do that. Let's call it C. Let's say C is this magical table where we can rate and keep track of things or solutions that we've done before. How can we implement that table to this recursive function? Oh, I did this too close to each other. Any one of you guys can say it.
Just with simple indexing, right? So like,
Where? First, tell me where would I?
yeah. So, I mean, you could, like, depends. What are like? Are we just putting the values in the table, or are we looking through the table for a value?
Yeah, we're going to be looking. We're going to first check if the table already has the value n and m, and if it does, return that number.
So with the values in the table, I'm gonna pause there, there you go. the values on the table start from 0 to n? So 0.
Yeah. Okay, you're actually thinking of it as a matrix.
Yeah.
I was trying to go at it as a hash table,
Oh.
but it's fine. No, it's fine.
I was thinking about it as a matrix.
Yeah, if it's a matrix, it's all the same thing. You can just go from 0 to n, or 0 to n, and then 0 to m. Let me draw it out so we don't forget. So what now? What do we want? What do we need to add here if we have this table?
If we use the 2D array of integers, they're all initialized.
Yeah.
Initialized to 0.
Yeah.
Yeah.
Let's just do. Now it looks like a crosshair, but that's fine. You know what? Let's not do that. Actually, let's just verbally say they're all initialized to 0.
Yeah.
You would return it as a calculated on that one.
Where?
Well, I mean, you could return, like in the if n equals 0, n equals 0 to return.
Yes, you're right. We can add it here, but let's just return
Okay,
0.
yeah, we'll just leave it like that. So if the value in the table is 0, that means we haven't worked out it yet. So we have to go through the whole function. But if it's not 0, we can just return that tabulated value, so we don't have to recursively call the sub-problems again.
So what David just said is, if in the table at position nm, if it's equal to 0, we know that we have not found an answer currently for that nm position, and we might have to go through this. But if it's not equal to 0, we have done the work before, and we could just return that work, which is exactly right. So if we look at our table, this is another if statement right here, right below our base case. If c of nm does not equal 0, then we know that we have done the work before, and we want to return whatever answer that is. So return c at position nm. Does this make sense to you guys? Yeah?
Oh,
No?
No, I actually don't understand it yet.
Okay, cool. That's fine. So do you understand why we're doing that, why we're checking that it does not equal to 0?
To make sure there's actually something in the...
Exactly.
Yeah.
So initially, this is the table is full of zeros, right?
Yeah.
So if it is equal to 0, we know we've never done the work before. That part makes sense?
Yeah.
Perfect. So if it does not equal to 0, we've done the work before. Therefore, if we know it's not equal to 0, let's just return that number, that work that we've done before, and let's not do it again.
Okay, yeah. No, I understand now. Yeah.
You-
The return would obviously leave the...
Yeah, exactly. And the return will cancel out, and we don't have to do these calls.
Yeah.
I think I know what your next question is, but yeah, say it.
Why n and m? Like, why that position in the
Oh, yeah,
matrix specifically?
It could be
I mean,
the rows.
I know the answer, but like...
Oh, okay,
Yeah.
okay. So he said why n and m, or he recommended that I explain why there's n rows and there's m columns. There we go. It could be flipped the other way around as well, because the rows just represents the number of characters in the first string, and then the columns represents the number of characters in the second string. It could easily be flipped the other way around. If it is, then you have to make sure you flip this as well, because you want to index specifically at that you want to index specifically wherever you currently are within that row, so anywhere from 0 to the length of s of 1, and then anywhere from 0 to the length of s of 2.
Are you confused that we're not using I or J?
No, I think he got it. He just recommended me to say it, right?
Yeah, to
Yeah.
explain why specifically he's returning the corner value.
Yeah.
Yeah.
So let's say n was 5, for example, which will be somewhere around here because we know that n it has a max of 8 and m has a max of 7. If it's 5 and let's say 3, so n is 5, we're looking at it right here, and then n is 3. What this is doing right here is checking that previously, if we have ever looked at these two positions in the past and we've done the work, let's return what that previous call came out with.
That's subproblem.
Yeah, what that subproblem responded with, or what was the answer to that subproblem. Thank you. And that's what we're indexing into n and m. Okay. Cool. So currently, they're all going to be equal to 0 because we're never saving our work. Where would we save our work?
You'd want to save it as you go, right? You'd want to save it in the you want to save it in the if else block as you go recursively through the problem.
Okay, perfect. Thank you. So as he said, we want to save it as we solve the problem. So for this first if statement, where would we add it? I would have to move things down, but
Yeah, that's what I meant by make space.
yeah, I made space for this, but not for.
Yeah, I was a bit confused when you gave space up there, but not down there.
Yeah, I gave too much. Yeah.
So
Oh, let me not. I'll erase this when you respond.
So here you'd wanna
Thank you.
when you wanna do it before the return statement.
Yes.
Yeah.
So he said, would we want to do it before the return statement?
Because you need more space for that to write it.
Yeah, yeah. No, that's fine. So before the return statement, we want to save this, whatever this gives us, in our table, but at what index?
At n and m, because we know that's the correct index.
Exactly. He said at n and m, because we know that's the correct index because that's the current subproblem we're looking at. Then, of course, after you have this work completed and saved, all you can do is just return that work. Perfect. Now we have one more. In the else, which you can look at it right here in case you forgot, we want to do something similar, but why won't you actually, come up here and write it out.
I need to think about it for a sec.
Yeah, that's totally fine.
Yeah.
Let me stand behind you so they can hear you.
Are we also doing the searching or just the indexing for now? Just
Yeah, for right now you only need the
just
indexing.
the indexing. Well, you don't index these because these are supposedly the wrong ones. So you just return the two.
But we want to save it. We still want to save that work done.
Oh, true. Right. So. Sorry.
No, it's fine.
Yeah. So at C, n, comma, m equals 0 plus solve.
So it's close.
It's close?
It is close.
Is it missing?
Yeah, you didn't need the second part.
Oh.
It's
Oh.
close in the sense where
Where's the, oh, right. Plus another?
not actually plus, but the maximum between going down one in the n or going down one in the m.
Okay, yeah.
Because you don't know which ones will be more effective, so you just want to get the maximum between either of them. Yeah. You want to write it out, or do you want me to write it out?
No, you're right.
Okay, okay.
I was going to put a semicolon.
Oh, Java.
Yeah.
Hey man, no semicolons.
Yeah.
This is Python.
I like the semicolons though. You need like, it's more readable that way, in a sense. Just a period? Yeah, it's kind of like a period.
There we go. So pretty much, can they see up to here? They could. So pretty much the exact same thing if they didn't match. Because all that we're doing is not that much of a difference. We're just storing the work and the answer we got for that subproblem.
With the indent. It needs to be indented. I'm kidding, I'm kidding. Alright.
There we go.
Thank you.
Okay. Java people, I swear.
Yeah. Well, it was Python actually.
No, he didn't indent it because he wrote it.
Oh.
So he didn't indent it because he writes Java. Okay, perfect. So all that we're doing is saving our work before we're returning. We're going to save our work in the current subproblem that we're at, which is n and then m. And here, this is absolutely no difference as the thing we had before. Before we just had return max of this. And here, we're just storing it in that subproblem within our table. And then we're returning whatever that was. Is this efficient now?
Almost.
Almost, okay.
Yeah.
I think it's pretty good.
Okay, it is pretty good. And yeah, almost. So big O notation of this is n times m, which is good, which is what we want. So this is an acceptable solution. You said almost because it's recursive. You could do it like a little bit better with a DP table, right? Or did you mean something else?
When are you like? Isn't it still like recursively looking through all the options though? Like,
No.
Look at that line. Second line.
So it's no longer going to do the work multiple times because of this line right here. If it sees that we've done the work before, it cuts itself early and it never makes the other calls. So it never reaches down here because we're returning and never does the external calls.
Why aren't you using a nested if statement to check the table to see if it's already been done?
Because it's nested. You can totally do that. Like you can do it in here if it's done before. Therefore, you don't have to call it, right?
Yeah.
But, and you brought up this argument as well. You could do it. The reason I didn't do it is because I would need nested if statements, and I personally don't like them, and I also don't have that much room. But if it calls itself, it's going to hit this if statement, it's going to evaluate this in constant time, and it's going to remove it, and it's going to terminate this call, this recursive call.
More recursive calls after.
So I understand what you said. It does make more sense. So you never have to call it again, but it doesn't really matter.
I used to think like that. Yeah. Like maybe I have to check another if. Like
Yeah.
maybe these sub problems are already solved.
Yeah.
in the table.
You had the exact same concern,
Yeah.
but it's a little bit cleaner without the ifs,
Clean thing.
without the nested ifs. So perfect. We got an acceptable solution of big O n times m, but can we do it non-recursively? By show of hands, who believes we can? Okay, well, that's 14 hands in the room. I'm kidding, only 7 hands. Be quiet, guys. So we can, there is a way of doing this non-recursively. by using for loops and using tables. Okay, David Acosta said yes in chat. Very good. So we're going to be giving this problem on Saturday. There's going to be a Saturday competition. And I'm going to challenge you guys to do it with a DP table. Or you can just look at Gary's lecture. I know Gary lecture, he did give the code for the DP table. He didn't give the code for the recursive, which is why I did it recursively. But he did give the code for doing it the DP table way. That's also on YouTube, so if you want to figure that out, you can just look at that video. Yeah, that's why I'm kind of not doing it. That's also why I'm not doing a DP table. I only have 5 minutes. But yeah, this is the recursive implementation. That's the code for that. On Saturday, there is going to be a competition. So I highly recommend that you guys try the DP table way in that competition. If it doesn't work out, then I guess you can resort to this, or you can always ask questions. I implemented a DP table way, and I'm pretty sure everyone else knows how to implement it as well. So we can help you guys out. Something else I want to bring up is LeetCode problems. We have daily LeetCode problems for both beginners and advanced programmers. The problems are sent out at 12 every single day. I highly recommend that you do them. We're going to be starting a thread called Solutions. Join the thread and then paste a solution to these problems in that thread. Or you can ask for help in the competitive programming channel as well. So I highly recommend that you guys do these problems, or just try these problems, because you might see them in an interview. They come from LeetCode, which is a huge database of interview questions. Other than that, that is it for the lecture. Hopefully you guys enjoyed, and hopefully you guys learned something new. I'll see you guys in the competition Saturday.